Hello everyone, it's July the 22nd. At the current moment, I am running a big suite of tests for my work, refactoring the code. It's actually been 3 weeks. I think it's been more than 3 weeks. I've been working on this project, trying to refactor and then improve the code. The refactor itself didn't take that long, but what really takes long is to find and to write a comprehensive, exhaustive test case so that we know or are confident that whatever change we make does not change the behavior. And that includes whatever bug was in the original code. We have to copy the bug. We cannot change the bug because there might be some features, some functionality that depend on the bugs. So anyway, this is a big test suite. I think it'll take about, 20 minutes to run, maybe not that long. Let's see, that run 20 minutes. Yeah, I think about right, 15 to 20 minutes to run. So I'll monitor it as I'm doing today's challenge. Okay, so today's goal. So first of all, definitely we'll try to finish this. It's a damn hard one, and then I have to check the solution. So last night after I finished it, we couldn't do it. So I tried for another maybe at least 20 minutes. I was trying, and then I couldn't figure out. Everything that I tried is all O(n) squared. So I'm now curious to see how you solve this in faster than O(n) squared. Anyway, do this first. Count the smaller numbers after self. You're given an integer array, and then you have to return a new counts array. Counts array has the property where counts I is the number of smaller elements to the right of nums I. So 5 we have 2 smaller. This will have 1. 6 we have 1. 1 have 0. Very interesting problem. Okay. Didn't seem complicated. Well, right off the bat, it's DP for me, right off the bat. So I'm gonna try DP first. Hold on. I need to prevent the screen from turning off. How do I do that? Battery. Where's battery? Battery, I see that. Battery. Turn display off. It's 15 minutes. Okay, so we'll do 15 minutes. Anyway, so we have 5, 2, 6, 1. If we go from right to left, the first one is definitely 0. That's deterministic because there's nothing more. In the second one, I look to my right and I see I have 1 smaller than me. And now we have 2. So 2, when you look to the right, we need to know how many that are smaller than me. How do I handle that? How many numbers do we have? Oh, I have lots of numbers. Yeah, we're thinking about like monotonic. But if I come in, how do I know? What if it's a monotonic array? If it's small, then I'm going to pop. So all those are bigger. So the next one coming in, if it's smaller, then yeah, we have everything. But if it's a big value, then how do I know? Right? It's a big value, it's bigger than this. So anything in between is bigger than this. Right? It's bigger than this, but it might be bigger than this, it might be smaller than this. Yeah, that is the thing. Hold on. What's monotonic array? So 6 coming in, right? So we move here. So we know that I am the biggest. So if 2 comes in, and I will pop 6, right? And then whatever's in between these two is larger than this. And for 2, all I count is the thing that's smaller than me. Okay, so that's 1. And now 5 comes in. Then I have 2. So monotonic might work. Let me think again. So we have, so monotonic means it's always increasing, right? So I want increasing from right to left. And I have a new thing coming in. If it's bigger than this, right, that means everything here is smaller. But what if there is something here initially, like let's say 1, 4, 2, 5. 5, 2, 4, 1. Now 5, 2, 4, 1 for 5, I need to do 3, right? And then if it's going to be 1, 4, and then 2 going to be pop 4, and then 5 comes in, right? And now at 5 we see, okay, I'm bigger than everything in this, but I can be a 4, it can be a 6, right? It will result in the same thing. If it's a 4, it has to count. If it's a 6, I don't count. Yeah, so just monotonic array by itself doesn't work. How about DP? Let's say if I know a certain value, the number that's smaller than me on here, so I have, let's say, n, x is smaller than me, okay? So I have a total, so we also know how many is bigger than me, okay? So now I come in, and I come in. If I am bigger than this, yeah, how about all those things? I don't know. Okay. I feel this problem has something similar to the one that I got stuck the other day, yesterday. They all have this seemingly good thing going on, but I just couldn't figure out, like right off the bat, I don't know. Okay, how about this? If I come in, and then if this number, if I'm bigger than you, then whatever is smaller than you is also smaller than me, right? Okay. So whatever is smaller than you. Now the problem is not the small, the problem is the bigger one. Oh, the test suite is done. 711 seconds, only 10 minutes. Well, I thought it would take longer. Okay, so that part is done. We'll deal with it later. Alright, back to our problem. What I'm thinking is, what if we also run, let's say, a monotonic array of increasing from left to right? If we run from left to right, what do we get? Like we have 5, we have 2, right? It has to be bigger. We want it to be increasing, so 2 is smaller than 5, then we discard. And then 6 is bigger. Six will pop 2. So by doing that, another prop, I have no idea. What the heck? I saw it in the past. hold on. Smaller. We can, hold on. Nah, that doesn't matter. So we want to see the number of small elements. Okay, so this we have the total number of small elements, but we also need its index to be bigger than me. So if so 3, this has to be 0, and I have a 1. How do I know if how many is bigger than 1? How many is bigger than 1? I want just given a list of array, I want to count the number of values that's bigger than some and smaller than some. Can we do that? If it's sorted, then we can binary search, but they're not sorted. Like a binary search tree. That might work. I feel it's very convoluted, right? If you use binary search tree for this. But we'll sorted it, right? So we sort nums, and we go from left to right. We start to build a binary search tree based on their indices. And as we build the index, right, it's going to be a binary search tree, but it is possible when we have some worst case scenario that it will take a long time. But what we can do is, and every time we'll take, if it's a worst case scenario, it will be a biased binary search tree. Then each time we insert, it's going to take on to insert. So that'll be on squared. So we pull back to on squared. No, I don't think so. I mean, I can cheat by using sorted list, right? I can definitely cheat that way, which cause insert is O log n. So basically O1 log n plus O1 log n. So O1 log n, I can solve this problem. I don't want to. That's I kind of cop out. There gotta be a method. It's actually the same problem. I want to know the number that's smaller than me. That's exactly the same problem as the original. You didn't change the problem at all. It's the same. I want to know the number of indices that's bigger than me, all right? And now we know the number of values that's smaller than me. Yeah, the two problems is exactly the same. It's the same, man. It's the same. All right. Do we have related topics? Segment tree. Segment tree. What? Segment tree? Nah, I don't like segment tree. Merge sort. Ordered set. Divide and conquer. Yeah, it looks like O and log in, right? Huh, no idea. Did I try? Did it myself? Maybe I did. Man, how? I don't want to use sorted list. Yeah, we can solve it, like if it's in a competition. Oh, if it's in a competition. Do they still have sorted list? I'm gonna cop out. I don't know, man. I don't know how to solve this. I don't know. Sorted container. Oh, we have to import it, I think. From sorted containers, import sorted list. Wait, a containers or a container? Containers. Hey, take the fun right out of it. Do I have sorted container here? I'm not sure. sorted container. Oh yeah, I have it. I have a cop out, and we'll see. Yeah, kind of. I mean, in competition, this works, right? But in interview, this doesn't work. So right now, basically, I just first solve this, and then, I mean, if you were talking about using this, maybe we can solve the other one using sorted list as well. But the API is the same, right? Just append, add. Yeah, we just need to add. I'm pretty sure the previous time maybe I also copped out. All right, so now it becomes very easy. Now it's a simple problem, right? From bisect, import, bisect, right? Doesn't matter which one you import. And basically, we will build, and then for each new one, we come in and bisect. We want to find that's smaller. So actually, maybe bisect left, right? And then whatever it gives you is the value. So we can say SL equals sorted list, and then res equals this, and for I range len nums -1, -1, -1, right? We can say res.append bisect left SL nums I. If it's smaller than, yeah, and then we say SL.add nums I. And return res. But how to solve it in reality? I have no clue, man. No clue at all. I hate this problem that we solved before, but I have no idea how to approach it again. Oh, what the hell? Oh, shoot. That is correct. Dang it. I have to run it here. Because the interpreter runs from global. Maybe we can prepend. Yeah, that's fine. Do they even allow me to pass? Oh, maybe they didn't even allow me to pass. No, they don't allow it. Even with this, they don't allow it. Oof. We can do that first. Yeah, we can condense it. Yeah, for sure. We can condense it. But still, I can kind of just say, yeah, this is another way to go. Right? You see, it's just telling you this is another way to go. I mean, we can condense it. So let's say we do like a counter. Okay? So we're talking about making it into a counter. Every time I put a counter in, and if it's inside, then we don't push. And what do we add? We have to know the total number in that range, right? Oh, total number in a range. Total number in a range. So if it's a new thing, we push it there, and we added it. So we know the total number, right? So this plus this plus this. So if we want a range, we just go there. Okay, let's try. Oh, yeah, but it's, no, let's do it the right way. Yeah, this is not working. Yeah, I'll give up. I don't know how to solve this. Segment tree. Jeez. What's the idea behind? Oh, it's just segment tree. How does segment tree work? We have a segment tree. Max and a minimum. Wait. Update. What's update? What does segment tree do? Segment tree will allow you to update a range and let you query a range in O log n time. So, hold on. Stop reading the answer. So, what it's trying to tell is I want to find the number of elements to my right that's smaller than me, which is just saying I want to query the number of elements from the smallest to me, right? So the segment, the total range is just the smallest to the biggest. That's the total range. and if I push 1, basically segment tree will update that thing. Ah, now it makes more sense. Now it definitely makes more sense. Segment tree. I'm gonna pull it off myself. Segment tree. Seg tree. I don't think I need. Oh, I need min max. Also need tree node. Left and right. Left and right. And count. But count is not gonna be here. Let's say self dot. Ooh, we have left and right in the conventions low and high, right? So range left, range right, range left, right, range right. So this one then R1 self dot range right equals this, and self dot left is none, self dot right is none, and we have self dot count 0. I actually did something using segment tree just a while back. Didn't work with the segment tree. Actually, I already forgot what method I used. But anyway, so segment tree, I have self dot root is equal to a tree node. Oh, we need to have a min and max. Min, R min, right? And R max. And that's gonna be R min, R max. Right? That's the root. And then we need to do def update. Okay. Update, give me the current range. Okay, so update range is range left, right? Range right, give me the current range. Can you give me the value as well? When I add a value to it. Actually, no. Why do you need a range? Update, we just need a value. And we don't return anything. Okay, so how do we update? Oh, we need a node. We need a node. It's gonna be a tree node. Maybe optional as well. So we need a node. So in this node, I want to update this value. So to begin with, if we have this node, we definitely have this node. Yes, we definitely will have a node, otherwise we cannot run update, right? So if in the end node dot this equal to node dot this equal to val, then node dot count equals 1. We should return integers, right? And now we return 1. Otherwise I say mid, right, is no dot this plus no dot this divided by 2, right? That's the mid value. And we say, maybe we can. Hold on, this is a mid value. And we say if value because it's left bias, right? So mid. If value is smaller or equal to mid, then we need to self.update no.left value. I do need a range. Otherwise, I'll say if not node.left, then node.left equals tree node node.range left and mid. And then we update. And we should say result return left equals this, right? If it's smaller than this. When I say return left equals 0, and now we do this, and then else return left equals return right equals 0, and if this, then else we say if not node.right equals tree node node.right no mid plus 1 node.range right, and then return right equals self.update node.right val. So after we're done with this, update is done, we say node count plus equal to no is equal to return left plus return right, not plus equal to, because we are updating. This gives me the total count on this. This gives me a total count on there, right? Even if I have something, what if I have something? So every time we push 1, right? And, ooh, that should be plus equal. Yes, plus equal. And we should return node.count. Is the current count, okay? The current count. If that's the current count, then we shall just equal instead of plus equal. So we're going to return node.count. So that's update. We'll also have query, which we just need to query a range left, right, range right, query return an int on node as well. All right, how do we query? Oh, we have this range. Then we're gonna say we have the node, we have a range, right? And then we are going to get a middle first. Query. If it's on here, then we query this. If it's on here, we'll query this. If it's in the middle, we divide it in half. We'll query this and query this. Okay. So eventually, we shall say if the node is equal to this, and then they're like this, they're equal, then we don't need to query anymore, right? So we say if node dot range left is equal to range left, and the node dot range right is equal to range right. Then we just return node dot count. Otherwise, mid equals node dot range left plus node dot range right divided by 2. And we say, what do we say? We say if range right is smaller or equal to mid, okay, range right smaller or equal to mid, then we're going to return self.query node.left, okay, and range left to range right. Nothing changed. If range left is larger than mid, then we're going to return self.query node.right, range left to range right. It's the same thing. Else, that means we're in the middle, then we're going to return self.query node.left, range left and mid plus self.query node.right, mid plus 1, range right. Okay, so that's our segment tree. And what do? We should say segment tree equals seg tree. Min nums, max nums. Okay, so I have the segment tree. Now we're gonna go from right to left. And the rest equals this. I in range len nums -1, -1, -1, right? For the first one, actually, yeah, we do need, right? So basically I say st dot update, right? Update the node I feel like the exposed API shall not have this node. This is like the internal thing. So I feel like we should have a def update val, and we should return self.update self.root val. Yeah, I would design it this way. So the exposed is much cleaner, right? So I just do this, and then we'll do this. And then def query self range left, range right, right? And then return int. And this will not return anything. None. Right? Because just update. We don't have to return anything. And then this one need to. So we just say self.update self.root. Not update. This is a query. RL and RR. Yeah, that's how I would design it. So just say st.update numzi and rest.append maybe I can use deck. Let's use deck. Okay. So I want to create a deck. So append left, right? Append left what? st.query. Well, query I need a range, right? So the range, actually I need to say min n max n equals min nums max nums min n max n. Then when we query, always query from minimum, right, all the way to me, which is nums I. What has to be smaller, right? So we just query it. Query will give me the total count. Then I update the query, update and query, and I return res. This I can run here. This is not right. Takes 2 position. Update takes 2 position. Update. Huh? Oh, my bad. Underscore. Underscore. Query is the same. Underscore. 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 It's an internal function. Nope. What happened? None type. Yes. So if we query and we haven't hit, if not node, I should just return 0. None, none, none. That is weird. That is very weird. Oh, because I forgot to return. 1110. That is weird too. And of course we cannot return res, so we have to list it. The update is not right, huh? I still need to. And I just realized I don't have to return anything this thing. I do this, and then I update the left, else update the right, and then equals node.left. Interesting. How about this? If this, then I always say node. Hopefully the most. I was going to minus it and then plus it. But let's just do this. If node.left else 0, right? So there could be this .left .count plus this node.right .count if node.right. Let's try it. There we go. Yeah, that was the error. Sec tree, this. Can run this. I'll definitely pass. Let's try this thing. One of those questions, right? It's not difficult. It's just segment tree. Yeah, it's just segment tree. I know this must be the BIT. Oh, you gotta pass. Come on. What? Dude. I never had this before. Oh. You cannot use. Oh, wow. You cannot use. Okay. Wow. This times out. You use node, it doesn't work. Is that what I used this initially? Yeah. Yeah, that one doesn't work. Wait, how far does this thing go? Sorted list. It went pretty far. Sorted list went pretty far. So I'm gonna try it again. Maybe we try it again, I'll pass. I don't know. So this definitely works. Right. TLE, this works, but still TLE, which means the OJ does not like to see the implementation of segment tree with actual nodes. What it wants is an implementation of using list to represent trees, which we can do. Yes, there's something we can do. So segment tree, we can do a segment tree 2. Okay, the logic will be exactly the same, so we can just put it here. So this is segment tree seg tree 2. Okay, and there will be no tree node. There will just be a tree. Gonna be a list. How long is this list? Well, let's see. If I say, let's say 1 to 5, okay? 1, 5, and then I have 3, right? So I have 1, 3, 4, 5. And then here we have 2, 1. So I have 1, 1. No, 1, 2, 3, 3. And then 1, 1, 2, 2. 4, 5, I have 4, 4, and 5, 5. Okay, so in total, I need 1, 2, 3, 4, 5, 6, 7, 8, 9. But then I have 1 level, 2 levels, 3 levels, 4 levels, right? So it's 4 levels. So that should be 2 to the 4th. I think 2 to the 4th minus 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. So that's 1, 5. Or if it's 1, 6. So should see the difference between. Difference is 5. So that's 2 to the second, 2 point some power. What's the generalization rule for this? The length of this thing. So we have a range, right? We divide it in half. That's one layer. Dividing in half, that's another layer. Dividing in half. So I see how many times I can divide, right? So for here, I divide all the way to 1. I divide it once, because we have plus is 6, so divide once is 3, right? And then 3 plus 1, 4. Divide, now we have 2. Well, 2 is 3 divided, we got 1. So we have divide that many times. How do I generalize this? So we say log 2 min plus max int plus 1. So min plus max, right, that's still 2. So 1, 7. How about 8? 8 shall fill, right? So like say 1 to 9. No, 1 to 7. So we have 8. So I have 1 to 4, 5 to 7, and then 5 is 2. So 1 to 2, 3 to 4, 5 to 6, 7 to 7. Nope. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. That's still 1, 2, 3, 4. That's still 4 levels. So if we go to 8, and that will be 8. That will be 7 to 8. Now we have 7, 7, and 8, 8. 7, 7, and 8, 8. That filled. So 1 to 8 fill the entire 1, 2, 3, 4 layers. So if we do 1 plus 8 is 9, right? And with log, that's going to be 3 plus 1, 4. But if we do 1 and 9, shall be the difference. Total number in between, right? If it's 1 and 9, that's 9. So it'll be 1, 5, and 6 to 9. So 1 and 5, I know this is already from here. have 4 levels. That's 5 levels. So it shall be, that's 2 to the 3 point something. So we are talking about a ceiling plus 1. So I think we're talking about R max minus R min plus 1. That's a total number of elements. And then we can say math.log Do I have log 2 on this? I actually don't know. I do. So we're going to say log 2 of this, and then math.ceiling this plus 1. That's the, I guess, that's the current guess. The total length. And we don't have, but we have index. So we start from 0, right? Query also start from 0. And we don't have node, we have index. And if we have index, and it's a 0 based, right? Then if it's 0, 1, 2, 3, 4, 5, 6, so that's going to be 2 times the index plus 1 is the left tree. 2 times the index plus 2 is the right tree. Okay? Okay. How about range left and range right? Do we have to store that information in this as well? I think so. So if that's the case, then I'll say it's going to be this. For this in range, this. Otherwise, I don't know the range. Okay, now I can do value. And then I say self.tree, right? Self.tree index 0 equal to self.tree index 1. Then self.tree index 2 plus equal 1. And mid, let's change this. Zero self.tree index 1. You can say R equals, right? And that's just gonna be this. We always have, so we can just update the left. It's gonna be 2 times index plus 1. We always have, so this is gonna be 2 times index plus 2, and then self.tree index 2 equals to self.tree 2 times index plus 1, 2 plus self.tree 2 times index plus 2, 2. Query. We don't need this. No, we do need index. Okay, again, repeat this. Ooh, we will call it underscore. Underscore. And so underscore equals this. Underscore equals this. Then we will return self.tree index 2. Otherwise, underscore, if this is smaller than mid, then self.query 2 times index plus 1. And yes. And this will be 2 times index plus 2. Otherwise, we're going to do 2 times index plus 1. And then 2 times index plus 2. Okay, so let's try secretary 2. Actually, we don't even have to change this. We just change the implementation of secretary. So I say secretary 2. And then we try it. Oh, index out of range. Oh, I forgot there should be 2 to the power of this. Ceiling of this plus 1, right? And this whole thing. Nope, still out of range. How? Wait, which one is giving me trouble? The first one. 6, right? 6 and 1, it's gonna be 6. It's gonna be it's gonna be 16, right? Max is 6 minus 1 plus 1 is 6. If we do log 2, it's 2.5. And if we take ceiling, that's going to be 3. And 3 plus 1 is 4. How is that not enough? Yeah. What is the index? Oh, I think I forgot to update. Oh, Jesus, man. Come on. Forgot to update. Okay, I do have to. So I have this and this. Ay, ay, ay. I forgot to update all of them. Damn. 0, 1 equals our min, our max. Ha. Okay, so that's my bad. Okay, so I do have to say, oof, 0. If I'm going to query there, maybe it's fine. I just do it every single time. I'm gonna do this. Say if self tree li ri 2 times index plus 1, 2 times index plus 2, right? So it's a left tree, right? If left tree 0 is larger than self.tree 1, that means this one has not been settled yet. If that's the case, then we shall say self.tree li 0 and self.tree li1 equal to what? Equal to range left and mid. And then we're going to update this. And we'll run the same thing here, but this time is right. Say if it has not been done, it's going to be like this. And then we're going to do the same thing as this thing, right? Same thing as this. We have to range right. And this thing can be replaced with Ri. This can be replaced with Li. And we do the same here. This is going to be Li. And this is Ri. Okay, let's try it again. Hey, still out of range. What the hell? The query part. Oh, I see. If this is larger than this, return 0. There we go. So it's a full translation of the previous segment tree. Okay, this one doesn't work. Now I'm gonna try this one and see if this one's any faster. 1504 the last time. This is slower. Dude, this is slower. And I think I did too many. Yeah, this is slower. Nah, this is too much. I need it to be just right. Okay? Just right. How many is just right? Gotta be a way to calculate. 5 is 9. 6. I don't want to do this. It's too late. What's the floor? Floor. Instead of ceiling, we do floor. Floor and then plus 1, right? Floor. Two times this plus 1. No. Oh, floor went out of range. What? And then 2 times n. No, I think it's because this doesn't have the left and right. Oh, I see. I see. No, it has to be ceiling. Has to be. I'll keep a ceiling. But you're saying we just do 0. Yeah, this seems to be a requirement. And then we don't need this. Then the update, we need a range. Okay. So the update will have a range. We have the index, value, range left, and range right. Don't we need the min and max? So we have to go self.min and self.max. Right? And we're we go. If this, then plus equal 1. Otherwise, that way 2, we have left and right. And then if it is this, we just go direct for it. Be this and this. Right, when update this range, and it turns out, wait, hold on. How do we update? So update this range, right? That's the initial. And then I say, okay, I can go this, and I need to update this. And then I need to update this, right? Basically, it's all dependent on the mid, right? The current range. And if the value is smaller, then we update this. Oh yeah, we just keep updating the range. That's not gonna be this. That's gonna be updating mid. And this is going to be updating mid plus 1. And R. Yeah, I don't know why I need this one. Doesn't make any sense. Right? I think we're done. We just say this equal to this plus this. And then we'll end when these two are the same. Yes, yes, that makes perfect sense. And in here, query, yes, we have this, we have this. Now when we query, that's a query index, right? The query range. So the query range and the current range. So we need 4 range, right? We need this is a query range and the R min and R max, right? So we have a Q query and a tree range. Okay, so these are the tree range. Actually, I already have this set up. I just need to do underscore. So these are the tree range. And then if this, I just return this. Otherwise, this equals this, this, this. Yeah, it doesn't change too much. So, this is the tree range. We have a mid, right? So we need to query if RR is smaller than mid, right? We're going to query this. Otherwise, we need to query mid plus 1 and this. Otherwise, we query that's the range, but we still need to query this. This is something doesn't change. Mid plus 1 and underscore R. Okay, so it's optimized. Let's try it again. Oh, jeez. Name army is not defined. Self. Oh, this shall never happen. Shall be if is equal to. Or they don't have to be the same, but this can be the same. Huh. Now we have too many. So I don't think this is necessary. I don't know. Weird, huh? Why would this one be 1? Yeah, I should answer that question. I really don't have a 1 value, okay? The max means the same. So that would be 1, be 0, plus 1, 1, the 1, 2 times. So I have only 2, right? So I'll update minus 1, okay? Update minus 1. I do think if this query, hold on, querying this, Oh, this is important. Thing we try to query. Okay. That is yet another implementation. All right. How about this? Are you happy with this? This is still slow. So what's the difference between this and this? Okay, I can see a little bit difference. That's the update code of this. Mid, if it's smaller, then we query this. Otherwise, I'll query this. Okay. 0. Then this. Query this. Query this. And we add them together. Alright, the only difference is I use a... No. Seriously. Really? You gonna do that to me? Man. Based on an array representation of a binary tree. Yeah, I already know what to do tomorrow. Have to try the BIT. Okay, this is fast. But the other one is also fast. No. Are you kidding? You kidding me? You're killing me, man. You're killing me, man. The ones that passed last time don't pass again. Oh, man. I have one of them. Is that this one? One of them passed everything. No, not this one. I think it's probably the second one. This one passed everything, but they still failed me. Yeah. Alright, you want to try this one again? Oh, yes. Yes. let's try this again. Let's try original. Okay, so don't say anything. So this is uses tree node based segment tree. Yeah, that's the benefit of this. Like, I don't have to change anything. The implementation doesn't change, right? What changes is the tree, how you build a tree. Now we're gonna go back to this one. Okay, the original one. Let's see. I remember it runs like 1,400 something. Now I have 2,000. But keep in mind, I use this, so it shall be faster. Let's try it again. If it still fails, that just means it's just not working. I have to go BIT. I was actually trying to do BIT tomorrow. Yeah, it's not working. All right. None of these works. Ah! All right, the big gun, big gun. Damn. Okay, BIT. The logic on BIT. The size. Update. Position. Okay, it's just a value. And delta is just by adding, update that value by 1. All the other range including. Is. But in my case, it's just 1. Okay, so min max, so that's not going to be segment tree. I'm going to do BIT. BIT max minus min plus 1. Then BIT.update. Position and delta. Position, that's the position. Delta has 1. And query max R. Ooh, update has to be the position. We have the minimum, right? So it's from minimum to this. How many positions? So happy this one minus main n plus 1. That's the position. And the query is going to be this minus main, not including me. Okay, try it. Pass. If bit still doesn't pass, then I have no clue what to do. Throw everything at it. Okay, bit shall pass. Oh, that's not tree bus. That uses bit. Damn. It's about 1,000 more. Holy crap. Holy crap. Hi. It is in the nightmare. It is a nightmare problem. Still a nightmare problem. Didn't change. 315. Alright, I tried segment tree with tree node implementation. Timeout. TLE. With array implementation. TLE. With the same implementation as my previous attempt, my attempt last year. TLE. The only thing that worked is bit. Maybe it's time. Maybe it's time to revisit bit again. To revisit bit and try to understand it. I know there's a post to understand, but okay, I'm mad that I did not see it's it's segment tree. Yeah, but I am disappointed and mad actually that I failed to realize the problem is a straightforward segment tree. And log in. Alright, that's it. That's enough. I think we will have to spend some time digging with bit again. Lordy monstrosity. Alright, I'll see you guys tomorrow. we haven't even touched. Jeez. Alright, adios.